All right. Hi everyone. Nice to see so many faces here in Copenhagen. My name is Anders, and I'm happy to present my work on real-time speech modification using neural networks, so to say. I chose to call it Reshaping the Voice. Basically, it's just a summary of what I've been doing for the past 3 years as part of my PhD project here at Aalborg University, together with a company called Hacker VR. Let's just get started. I'll talk about voice conversion, voice transformations using AI, neural networks, deep learning, call it what you want, and ask how such models may be used practically, first of all, and also how they can run in real time and be designed to be deployable. And then you may ask, what is voice conversion? I guess most of you know about it, but in short, it's the act of changing the voice of someone without changing the words and the content. So that could be me saying, hi, ADCx, and after being processed by this AI neural system, we can see it as a gray box for now. It sounds like Taylor Swift saying, hi, ADCx, or whatever. And of course, someone may associate this with very unethical use cases, fraud, phone calls, scam, what have you, but actually the problems and challenges tackled within the voice conversion space spans the wider voice tech landscape, from more text-to-speech, navigation, instruction summarization, audio books, reading out loud, to the more creative and interactive things like vocal dubbing, vocal editing that has a speech input, of course, to something like choir arrangements in music production in a DAW. And I guess it's the more creative, interactive field over here that we are interested in. You may have heard about the big players in the game, 11 Labs, Resemble AI, OpenAI, ChatGPT, what have you, and they provide super realistic and incredibly high quality speech audio, but they have some inherent limitations. First of all, they are parameter heavy. They are really large, needs millions of operations per second, so we can't really run them in real time. They also are built on non-causal processing. That means they require information about the future to process the current step. We don't have that when we are streaming audio unless we have a look-ahead, which we may not want due to latency. They are unforeseeable, so we can't really know what they will produce, and they're non-controllable. So voice cloning is target-specific. You can't maybe go in and change the duration of the voice or the rhythm or the pitch or what have you. So in order to take account of that, I want to take a small leap into music timbre transfer, which is the act of taking an input monophonic sound and make it sound like an instrument. And this is interesting because in the music domain, we have had much more focus on real-time requirements due to the fact that they need to run in a DAW. We want to hear the processing straight away, so we want a very low input-output latency. Maybe you also want to jam with other people. So it's very important that they can do this. And the way that they do it is mostly by combining neural networks and signal processing. So you have a neural network that predicts a filter coefficient or parameters for a synthesizer or something like that. A known approach is DDSP, where we use a neural network to predict parameters for a harmonic additive synthesizer. So here we have a model that's trained on a lot of flute data. So if we take this input violin sound here, input audio, we're continuing, we will have a flute sound sounding like this after being fed through the model. There are also other models like stable audio where you can prompt stuff. This doesn't run real time, but it adds some flexibility by prompts. So we can say, make it sound like a trumpet. And we can also look into something called Rave, which is built on audio compression, where we here have a model that is built on voice, which will sound, here a female voice, which will sound like this. So obviously these models here in the timbre transfer domain, they are real-time capable because they are quite small and use a mix of neural networks and DSP. They have streaming audio, they are controllable in some sense, but they have no notion of words. They are completely unintelligible. They are model dependent, so you need to train a model for each instrument, which doesn't really make sense, and then they lack expressivity. There's something with the quality due to them being small and designed to run in real time. So I tried to sort of combine speech representations with timbre transfer to basically create voice conversion in real time and make it possible for these models to have a notion of words as an example, and thereby make them intelligible, also give them a notion of identity, so make them model independent, and also add some machine learning, let's say, tips and tricks to make them high quality. And the way that this is working is through something called disentanglement. So we take an input audio sound and then we extract a lot of different features from which we learn to reconstruct the audio input. And that is done with the white box here called the decoder. And you could use a lot of features. I chose these 4 features here. And if it seems a bit complex, I like to sort of explain it as an auto mechanic that takes a car and disassembles it into wheels and steering wheels and window and motor. And then another auto mechanic comes in without any knowledge of the car and tries to assemble it together again. And over time, they've seen millions and millions of cars and learn how cars kind of work together. It's kind of the same with audio. You see a lot of speech data and learn how to disassemble it and assemble it together again. And once you have done that, you can kind of manipulate each individual aspect. So here I've chosen to represent timbre as identity. So that's like a vector that's related to the timbre. It could be pitch contours as an example, loudness contours, or phonetically irrelevant information. And yeah, you can then manipulate it once you've disentangled it. And of course, in real time, switch between different identities, add a manipulation to the pitch. That could be an LFO, or it could be a shift to make a pitch shifting. So let's try to see how that sounds here. Just have a small example in a DAW where it runs in real time, streaming just an input audio file, and I change between different identities.
Essential in producing this filling out of sensation, but not the recollection.
Loading. Let's just see here.
The fact of past experience is essential in producing this filling out of sensation, but not the recollection of past experience.
The fact of past experience is essential in producing this filling out of sensation, but not the recollection of
past experience. The fact of past experience is essential in producing this filling out of sensation,
but not the recollection.
So yeah, here in the end, we just hear the dry wet being somewhere in the middle, and we can hear the input-output latency. To have some more creative examples, let's look at singing voices as an example. You can take an input audio file,
I did it my way.
Add a target, so an identity.
We also need a small plastic snake and a big toy frog for the kids.
And of course, process it.
I did it my way.
And then since we have everything disentangled, we can add several decoders, several identities, several pitches, and maybe create a choir.
I don't care about anything. I don't care about anything.
And
I don't care about anything. I don't care about anything.
All right. So let's move on to some of the sort of technicalities. I mean, this is not a machine learning conference, so I won't go deep into the networks, but each feature here is extracted by pre-training a network to do so. So as an example, we have encoders that are based on convolutions. They downsample the input audio to solve a specific task. So the timbre is sort of extracted by solving a speaker verification task. We have a lot of different speakers and we learn, okay, this vector can be related to this speaker. Whereas linguistics are extracted by predicting something called speech units, and they come from these large foundation models that are trained on millions of hours of speech data. And then someone found, okay, the 11th layer in this model is related to phonetic information. So we can predict the output from that layer and basically have something related to linguistics. In terms of loudness and pitch, as you know, we could just use DSP. I chose to use also an encoder because I like machine learning. And basically what that encoder does is extract F0 information, loudness information, information about the periodicity. And from that, we borrow actually what we saw earlier from the DDSP model, a synthesizer that is harmonic and additive, and then create sort of an excitation that drives the whole synthesis process. And then you can see the decoder as a very clever filter that, based on the identity and the linguistics, filters this excitation here. So you can say that when you also, I guess, add some manipulation to the excitation, that will be reflected in the output as well, as an example by pitch shifting. Last technicality, why is it streamable? Well, as talked about earlier, the big models that we know about are non-causal. So that means if we look up here at Y3, it does not only use X3 to get Y3. We use the two former as input samples, but also the two future input samples, which means we use also the next input hidden state. And of course, if we don't have a look ahead, we can't really do that in real time. So we needed to make sure that the models and the convolutions that we see here are causal. So we only use the current and the former samples. And then in order, I mean, when you have convolution, you also need maybe to fill up the kernel with the samples that you need to perform the convolution on. So you would do padding as an example. We can't do that either. So what you do is that you cache both the former samples and the states from the buffer and add that to the next buffer when you sort of perform the iterative processing, right? And that's a very, very important aspect of making these neural networks based on convolutions, at least real time. The plugin pipeline looks a bit like this. All the model stuff is happening in PyTorch where we train it. Then you export it into a Torch script export so that it can run in real time in a C++ framework as an example. And then we do everything from input-output configurations, buffer writing, buffer reading, but host the Torch script model in Juice. And that also ensures that it can run with quite a low latency. The model, of course, is quite small. That's important. We only need one buffer to process it. We don't need a look ahead. And then due to the fact that we can import it as an example in Juice and use Juice for all the clever and fast buffer writing, we can have a quite high real-time factor on this VST here. Here's a more illustrative overview of how it looks. So when we train the model, everything is happening in PyTorch here in gray. But when we deploy it, we take actually most of it and use C++ and Juice for that, hosting only the machine learning model in Torch scripts. So here, this is just maybe a last example of the overall system. I just want to show a use case that I used it for. So we added it into Unity, where we used sort of Unity to create voices for 3D avatars and like a voice design framework for avatars, where everything from control and UI is happening in Unity, as you see here at the top. Then the Juice is exporting the model and all the audio stuff to a Unity build that then can be hosted in Unity. And then that build is then having the sort of PyTorch model in it, right? So maybe we should conclude with an example of how that sounds. I added a virtual reality head here because it was meant to work in virtual reality, but I guess the main idea is that it works in Unity. So let's just see if that works. That would be lovely.
Recording my voice. 1, 2, 3.
Recording my voice. 1, 2, 3. Recording my voice. 1, 2, 3. Recording my voice.
1, 2, 3. Recording my voice. 1, 2, 3.
Recording my voice. 1, 2, 3.
Recording my voice. 1, 2, 3. Recording my voice. 1, 2, 3. Recording my voice. 1, 2, 3.
Recording my voice. 1, 2, 3.
Recording my voice. 1, 2, 3.
So yeah, you can hear that by manipulating all the disentangled features to rev up gives different output characteristics. And that's all from me. If you have any questions, make sure to find me. And I would like to refer to actually another ADC talk if you're interested in this topic. They also sort of present it very well. It's called AI-driven content creation. You can find it on YouTube, which is also super, super nice. Yeah. So thanks a lot.